Welcome back to Physics 142. In this video, I want to wrap up our discussion of magnetic induction by trying to understand why it actually works. Why is it that if you change the flux going through a hoop, if you change the magnetic flux going through some wire hoop, that you actually get a current in it? So, and I think that this actually is not very clear, not very obvious, right? So, let's think about what we've learned, right? What we've learned is that if I take and I have some current loop, and then I increase the magnetic field going through it, right? I increase the magnetic field going through it. What we've learned is that it's going to induce a current that opposes that change. So in this case, if the magnetic field if the change is up, opposing the change would be down, that would induce a current that goes like this, right? We would get some sort of current here induced. All right, so we know that happens, but why? And we might say, well, okay, we know magnetic fields provide forces, right? Forces ultimately, really the question here is what's getting these electrons going, right? The electrons are at rest, or the protons, right? Whatever's flowing, right? Your charged particles are at rest. What makes them get going? What makes them start flowing? And you might think, well, it's a magnetic force, right? That, the force from the magnetic field pushes on those electrons and makes them get moving, right? But there's a problem here. And the problem is that if we remember our magnetic force law, right? Force from magnetic fields is QV cross B, right? And what that is that the force is always perpendicular to the magnetic field and always perpendicular to the velocity, right? So if I want to increase the velocity, well, you can't increase the velocity when your force is perpendicular, right? If you're going this way and you apply a force perpendicular, that doesn't increase your speed, right? The only way you can increase your speed is by applying a force that's in the same direction, right? Or at least has a component in the same direction. And so magnetic fields, right? Magnetic fields can't do that. So it can't be a magnetic field that's actually providing the push that gets it going, all right? So, the question here is what provides the force, right? And the answer is, well, it can't be actually the magnetic field. It's not the magnetic field that's providing the force. So, well, then if it's not the magnetic field, what could do it? Well, the only other thing here that could provide a force on a charged particle must be an electric field. All right, it's not B fields, because they only push perpendicular. They don't make things accelerate, all right? They don't make these particles go, so it's not B fields. So what's left to push on charges? All right, well, it must be some sort of E field. All right, so it must be some sort of electric field. But, this electric field is going to be a little weird because it's going to sort of make things go in a circle, all right? And we haven't actually had any electric fields that make things go in a circle before, all right? But we know it has to be an electric field because it can't be a magnetic field and it has to push on the charges somehow, all right? So what I should write down here is, just to be clear, right, is that it must be then that if we change the magnetic flux, all right, that must create an E field, right, must create an E field or induce an E field, all right, which in turn creates potential difference. That is, pushes on the particles and gets them moving, all right? Pushes on the charges. All right, so it must be that somehow by changing the flux, we're creating a kind of E field that then can push on the charges and create this potential difference. And so I want to think a little bit about what this E field must look like, all right? And well, we know that if we're trying to get these particles moving in a circle, right, then the electric field that we induce needs to push on these particles and get them moving in that circle, right? We need to get them going somehow. So, depending on the choice of charge for what you have moving around, that means that the electric field goes one way or the other way, and it doesn't really matter because that's just definitional, right? So, I could think, well, the electric fields that would get particles moving in a circle, maybe they would look like this, right? They must be these sort of circular electric fields, right? That would be the kind of electric field that would actually make a push that would get things going in a circle. Because remember, electric forces, those go along electric field lines, right? Electric forces are along electric field lines. And this is very different from electric fields that we've seen before, right? Usually we're used to like having a positive particle, and the electric fields are radial, right? They either go in or out. I mean, I could make it a negative particle, then they go in, right? But the electric fields were going in or out. They weren't going in a circle, right? So clearly we have something very different here going on with this electric field that is induced, all right? And there's something else weird that's happening with this electric field, all right? And that is, well, what if we think about the potential? All right, so let's think about potential, and we know that potential is related to electric field, right? And that it was the opposite of the integral of E dot dl, right? And so what this says is that, well, let's imagine that we're down here and we start walking in little steps dl, sort of up the hill, right? Then what would happen to our potential? Well, our potential would be minus the integral of E dl times cosine of 180, which would be minus 1, which would cancel the minus sign. And so in other words, V, the potential that we gain walking up the hill, is the integral of E dl, right? Or E times the path that we walk up, right? That's how much potential we end up gaining. Maybe we'll call that V gain, all right? It's the potential from walking up the hill, all right? And we're sort of used to that, all right? But now let's think about what happens when we walk in a circle, right? Normally, if we walk in a circle here, if I walk in a circle, well, all my DLs would be perpendicular to these radial vectors, right? And then I'd have a cosine 90, and so if I walk in a circle, normally I don't gain any potential, right? But now, if I walk in a circle in this kind of electric field, right? If I walk in a circle here, well, I'm gaining potential all the time, right? I guess maybe I'd be walking against the field, right? So maybe I walk this way, right? So walking against it, that's walking uphill, right? So I walk uphill against it, and I walk and I walk and I walk, and I keep going. I keep gaining potential as I go. I keep going, all right? And so this is a little weird because this means that Kirchhoff's laws laws don't apply here. What do I mean by that? Well, I mean that if I start at a spot and I walk in a loop and get back to where I started, I'm now not at the same height. I've climbed uphill and now I'm at a higher spot, and every loop around I go further and further up the hill. That's a little weird, right? Here, I just walk around, I start at a height, I get back to where I started, right? Now, when I walk around, I'm constantly gaining height, I'm constantly gaining potential, all right? So what we say is that this electric fields that go in a circle rather than radially, these induced electric fields, we give them a special name. We say these circular electric fields are non-conservative electric fields, all right? So ones that go in a circle where Kirchhoff's laws don't apply, where you don't get back to where you started, right? When you go back to where you started, that's non-conservative, whereas this would be a conservative electric field. And so what we get from all of this is that what's creating this current, all right? What's creating this current, well, the induced EMF, all right, is going to be basically whatever V we gain when we walk around the circle once, right? It's going to be whatever v we gain, and that's going to be the integral over a closed loop of E dl, right? E dl, and I guess I should make it a dot product to be clear, right? We go in a circle, but it's only the part that's in the circle. So I should actually write this, rather than EDL, I should write this as the non-conservative electric field, right? It's the non-conservative electric field dotted with DL. That's how much potential we gain when we walk around this loop, all right? Because when we get back to where we started, we're going to be at a different height. And I should just point out then that this means that we have another way of writing Faraday's law, right? What we can write is E induced is minus the change in flux with respect to time. So what we can write, and I'll write it in red, all right, a new way of writing Faraday's law, is we can write that minus d dt of phi, all right? So that is the change in the flux, must be equal to a closed integral, all right, that is, if you walk one full circle, all right, in this field of E dot dl, all right? And so now we have a direct relationship between electric fields and changing magnetic flux. If we change the magnetic flux, you change your magnetic fields, that's going to create an electric field, which it's the creating of the electric field, creating of this non-conservative electric field, which ultimately is what's responsible for getting a potential difference and thus a current. So I think that's pretty cool, and we will get into this in more detail in coming lectures, but I think it's just really important to recognize that what's happening when we're inducing a current is actually the flux, the change in the flux is creating an electric field, and that electric field then is what's creating the potential difference, which is what's creating the current. So there you have it. That's what's behind this. And I think I will leave this video there.